Example 1c. Add the rational expressions 2 over 5x squared plus 5x plus 4 over 3x plus 3. These are rational expressions with unlike denominators. We first have to find the least common denominator. So let's take a look at our first denominator. Our first denominator is 5x squared plus 5x. Let's factor this out. 5x squared plus 5x is 5x times x plus 1. We achieved that by taking out the greatest common factor of 5x from each term. Let's look at the second denominator, 3x plus 3. We can factor this by taking out the greatest common factor of 3 from each term. So we're left with 3 times x plus 1. By factoring out, we are now able to see the least common denominator. Our least common denominator consists of a factor of 3 and a factor of 5, or 3 times 5, a factor of x, and a factor of x plus 1, which appears in both factorizations. So our least common denominator is simply 15x times x plus 1. Now we move on to step 2. Step 2 is to change each rational expression to have this new denominator, the least common denominator, 15x times x plus 1. So I'm going to rewrite my fractions, again leaving space. I have 2 over, and when I rewrite, I'm actually going to rewrite it so that the denominator is factored out. That's 2 over 5 times x plus 1, or 5x times x plus 1. The second rational expression is 4 over, and again I'm going to factor this out when I rewrite it, 3 times x plus 1. Good. We want these two fractions to be changed into equivalent fractions that have our new denominator, our least common denominator, 15x times x plus 1. So we'll have new denominators in both cases. So what is it that we need to multiply by in our rational expressions up here to obtain these new least common denominators? Well, let's see. 5x times x plus 1, we want to get it to be 15x times x plus 1. To change the 5 into 15, we're missing a factor of 3. In other words, we need to multiply the 5 times the 3. And if we do it to the denominator, we have to do it to the numerator. That'll give me 15. The x and the x plus 1 are already present, so we don't need to change or multiply this by anything. And that tells me the only thing we needed to multiply by was a 3. So in the numerator, 3 times 2 is 6, and that's our new numerator. We now turn our attention to the second rational expression, 3 times x plus 1, and we want to change it into 15x times x plus 1. Focus on the number first, 3. 3 needs to get multiplied by the factor of 5 because 5 times 3, or 3 times 5, is 15. So we need to multiply our numerator by 5. The x plus 1 is already present, but we're missing this extra factor of x. So we'll also need to multiply denominator and numerator by x. This tells me that the new numerator is 5 times 4 times x, or 20x. We're now ready to proceed because we now have like rational expressions, and we can put these rational expressions together by combining the numerators and keeping the denominator the same. So we have 15x times x plus 1 in the denominator, our least common denominator, and in the numerator we have 6 plus 20x. And I tend to prefer to like to put my variable term first, so I'm going to rewrite that as 20x plus 6. Is there anything that can cancel? Well, let's see. If there's anything that can cancel, it appears as a factor in numerator and denominator. So let's first try and factor out the numerator and see if anything can then cancel with the factors in the bottom. So let's factor out the numerator. Notice we have a 20 and a 6. The common factor of 20 and 6 is simply the number 2, so we could try and take out the number 2. So let's try and take out the number 2, and when I do, I'm left with 10x plus 3. Looking at that, with the numerator in factored form and the denominator in factored form, is there anything that you see that can cancel? The answer is no. 2 doesn't cancel with 15, 10x plus 3 does not appear anywhere down here, and x plus 1 doesn't appear up here. So that means that our rational expression is already reduced to lowest terms. We can answer 20x plus 6 over 15 times x plus 1, or we can write it in factored form in the numerator, 2 times 10x plus 3. That completes example 1c. Example 1d. Add the rational expressions 3y over 2y minus 5 plus y plus 1 over 5 minus 2y. Our first step is to obtain the common denominator. Notice that 2y minus 5 and 5 minus 2y are different, but they're also very similar. Let's write down our first denominator, 2y minus 5. That's factored as far as it can go, so we'll just write it as 2y minus 5. Let's write our second denominator, 5 minus 2y. I say they're similar because notice they're both subtraction and have the same terms. The order is simply flipped. And what does that mean? Well, we've done this before. When the order is reversed in a subtraction, it simply means that we could make this expression look like this expression by factoring out a negative 1. So let's do that. 5 minus 2y. I can rewrite that as negative 2y plus 5 if I put the variable term first. And by doing it this way, notice I now see there's a negative sign that I can factor out from the front. I'm going to factor out a negative 1. And when I factor out a negative 1, I'm left in the parentheses with 2y minus 5. Negative 1 times 2y is negative 2y. Negative 1 times negative 5 is positive 5. That means that our least common denominator is simply 2y minus 5 times a factor of negative 1. So our LCD, if you like, is simply negative 1 times 2y minus 5. We now want to rewrite our rational expressions to have this new denominator. Let me begin by rewriting the first rational expression, 3y over 2y minus 5. And that we're adding to y plus 1 over, now instead of writing 5 minus 2y, this time I'm going to rewrite it in its factored form where we pulled out the negative 1. So 5 minus 2y is equivalent to negative 1 times 2y minus 5. And if we want to make this our least common denominator, we want to change both of these to have the least common denominator. So we want to rewrite these so that they're on top of negative 1 times 2y minus 5. What is it that we need to multiply by to change each of these fractions to get this new denominator? Well, in the first case, in the first rational expression, notice what we're missing is the factor of negative 1. So when I multiply the bottom by negative 1, I also multiply the top by negative 1, and that creates in the numerator negative 3y. Now this rational expression already has negative 1 times 2y minus 5 in the denominator, so I don't need to multiply by anything here. That is, I can simply rewrite my numerator and it stays the same. We now have like denominators and we can put this together. Combine by adding up the numerators. We have negative 3y plus 1 all over negative 1 times 2y minus 5. Continuing to simplify, what does that give us? That gives us negative 2y plus 1 all over negative 1 times 2y minus 5. Now, if you're doing these problems and you look and compare your answer to My Math Lab or to the back of a book, you might see something slightly different. A lot of places, they're going to cancel this factor of negative 1 from the bottom and the top. So why don't we go ahead and factor a negative 1 out and then see if we can cancel it and get an equivalent answer. So let's factor out a negative 1 from the top. When I take a negative 1 out from the top, I get 2y minus 1. Let's check. Negative 1 times 2y is negative 2y. Negative 1 times negative 1 is plus 1. The bottom is negative 1 times 2y minus 5. And now observe, this factor of negative 1 appears in the numerator and the denominator, so it can be canceled. And so this is equivalent, this rational expression is equivalent to simply 2y minus 1 over 2y minus 5. So let me box this answer. 2y minus 1 over 2y minus 5. This is probably the answer that you'll see in the back of a book, or which MyLabs Plus will give you. But this is equivalent, and notice we could rewrite this guy over here if we wanted to. It's equivalent to negative 2y plus 1 over negative 1 times 2y minus 5, which remember is simply 5 minus 2y. So you might also see this answer written like this. And these two are the exact same thing. They differ by a factor of negative 1. So let me also box this answer. That completes example 1D. At this point, I do want to tell you that there's an alternative way to solve these problems, meaning problems where your denominators differ by a factor of negative 1. The book goes into an explanation of this, so I'll let you look at examples from the book in order to do that method. Hopefully this one made sense for you as well. We move on to our last example in this topic.